So now I want to look at this K, this equilibrium constant expression, a bit and talk about some of the rules that are associated with it. The first thing I'm going to do is show you that when I write down a reaction, I do not always include in this reaction all of the terms that are shown. So here's a reaction here involving water dissociating to make protons and hydroxides. You might think that when you write K, that what you would include is the stuff on the right over the stuff on the left. But would you be surprised if I showed you that K equilibrium is actually equal to H plus times OH minus, and I do not include the water term at all. The reason for this is that we only include in our equilibrium expressions those terms which are capable of changing. It turns out that pure liquids, like water in this particular case, have a constant concentration. You can figure out that constant concentration, and we'll do this later on. But basically, if I have a liter of water, that's about 1,000 grams of water, which is about 55.4 moles of water, which means that I have 55.4 molar water. In other words, that value right there is 55.4 molar. Well, if it's 55.4 molar, then that's a constant. And if it's a constant, then I can roll it into the equilibrium expression here, so that the only two values that are changing are these values here for the amounts of protons and hydroxides dissolved in solution. So what's the general rule then with respect to what goes into an equilibrium expression? Well, I'll show you four categories of materials, and we'll figure out which ones of those can change and which ones do not. What about the pressures of gases? What about the concentrations of solutions? What about the concentrations of neat liquids, pure liquids? And what about the concentrations of solids? If you look at these, four of these are capable of changing their concentrations, and, two of these are capable of changing their concentrations and two of them do not. Obviously, solids have a constant concentration throughout, and neat liquids, as I just showed you with water, have a constant concentration. We end up assuming that the activities for these are equal to 1, because we can roll whatever their concentrations are up into the equilibrium constant. It is only these two values here, the pressures of gases, because gas pressures can certainly change in a system. They can become higher pressure, lower pressure, and molarities, the moles per liter, that can change. This means then that if we take a look at any kind of reaction, and I'll just show you a couple examples here. You can see that when we set up the equilibrium constants for these, I would not include this solid right here. So K equilibrium would just be the sodium ion concentration times the chloride concentration. And I would not include the neat water here. I would include the gases that change, so that K would be equal to the hydrogen gas concentration squared times the oxygen concentration. So it's important to keep this in mind when you're creating your equilibrium constants. And just basically, if you see a solid, ignore it. If you see a pure liquid, like water typically, you ignore it.